Let's take a look at section 4.5. Here we're looking at the mathematical model for exponential growth or decay. And that will always be a model of the form f of t. So time is our independent variable. Our function could either be named f of t or it might be named a of t. Time is our independent variable. We have some initial value that here we're referring to as a sub 0. So that could be an initial amount, an initial size, times the exponential e to the kt. K is called our growth or decay constant. And if k is positive, the entity is growing. If k is negative, the entity is decaying. So this is the exponential growth or decay model. Notice that when k is bigger than 0, because it's representing exponential growth, the model is increasing. As you move to the right with your time value, so as time increases, the value or amount increases. So if you are at a point on the graph and you move to the right, you have to go up to get back on the graph. And that will always be true wherever a function is increasing. When you're on a point on the graph and you make a movement to the right, for an increasing function or an increasing portion of a function, you then have to move up to return to the function. Now, when k is negative, we have exponential decay. So if you are at a point on the graph and you move to the right, you now have to go down to return to the decreasing function. So whenever a function is decreasing, or whatever portion of a function is decreasing, if you're on the graph and you move to the right, you have to go down to return to the graph. Let's look at some examples. Here in example 1, we have a colony of bacteria that is increasing according to the law of uninhibited growth. So we call an exponential function a model of uninhibited growth. So the growth just is continuing and continuing at a rapid rate. Now what we find in reality is that nothing can grow uninhibited. So there's always something that eventually inhibits growth. So usually these models are only realistic for a portion of time, but that doesn't matter for us here. All right, so our amount of bacteria is a function of time. So I'm writing the function a of t. And it doubles in 5 hours. So this means it's growing. So we know that that means our k is going to be positive since it's exponential growth. So when t equals 5, and we can also just refer to this as a, just for simplicity, a becomes twice whatever we began with. So remember, a sub 0, sometimes referred to as a naught, is the initial amount. So we can replace this a on the left with 2a sub 0. And we can replace t with 5. So notice the only unknown is k. So this allows us to find k. So if I divide both sides by a sub 0, I see that that is actually a factor, when I have the information that I have, that drops out of the problem. And now I'm going to be able to find k. I'm going to do that by applying the natural logarithm to both sides of the equation. So the natural log of e to the 5k is the exponent I have to apply to e Remember, natural log has an unwritten base of e. So this is the exponent I have to apply to e to get e to the 5k. And so that result is simply 5k. All right, so the natural log of 2 equals 5k. And to solve for k, I simply need to divide both sides of the equation by 5. And so I find that k is the natural log of 2, whatever that is, divided by 5. And notice how important it is to write this carefully so that the ln is above the fraction bar. Notice that would be completely different than if I wrote this. So this means the input to the log is 2 over 5, which is different from taking the natural log of 2 and then whatever that number is, dividing that by 5. So make sure you write with care so that you write things correctly. All right, now technically I could find this if I wanted to, or I could leave it in this form. I'm going to go ahead and approximate it. So I find that this is approximately 0.138629. And I can just leave it in that form for now if I want. All right, so that allows me to answer part A, which is asking me to give the function that describes this situation, given that the colony of bacteria doubles in 5 hours. So my amount at any given time is whatever the initial amount is times e to the 0.138629t. And the A naught will have to be specified for a particular problem, as we see in part B. So if there are 10,000 cells initially, how long will it take for there to be 25,000? So I'm going to replace A with 25,000, and I'm going to replace A naught with 10,000. I'm just going to check back that, okay. And that is going to allow me to have only the variable t and to solve for that variable. My goal is to isolate the exponential. So I'm going to divide both sides of the equation by 10,000. So I wind up with 2.5 equals my exponential. And right now I'm just going to put k in instead of this long value of k. kt. We know what k is, and I'll fill that in later. And now to solve for time, I'm going to apply the natural log to both sides. The natural log of e to the kt is the exponential I apply to e. The base of this log is an unwritten e to get e to the kt. So the exponent I apply to e to get e to the kt is kt. And so the natural log of 2.5, if that's equal to kt, and if I want to solve for t, which is what I want to do, I simply need to divide both sides by k. So t is natural log of 2.5 over k, and now I'll go ahead and fill in my value of k. And I am going to approximate that using my calculating device. And I see that this is about 6.6 hours. So it takes about 6.6 hours for a colony of 10,000 bacteria to increase to 25,000 bacteria. And the thing is, we know that makes sense because we were told in Part A it takes 5 hours for it to double. So we know 25,000 is slightly more, is about 1.5 times, or 2.5 times, 2.5 times 10,000. So we know that we need to get something greater than 5. We know that we're more than doubling this. So we have a sense that this is a reasonable answer. So that's problem 1. Now in problem 2, a bone is found to have 45% of the original carbon-14, and the half-life of carbon-14 is 5,600 years. How old is the bone? So before we even start, we know our answer is going to be less than 5,600 years, since the half-life, the time it takes for there to be half of the original amount is 5,600 years. And we know 45% is less than half. So we're using the exponential function, the amount of carbon-14 equals the initial amount times e to the kt. And we need to find k, which we know is going to be negative since this is decaying. So the half-life t, which sometimes is referred to as h to represent half-life, is 5,600. So when we're at that time value, a is 0.5 half of the initial amount. So we're going to go into the function, and in place of a, we're going to put 0.5 a naught. And that is going to equal a naught e to the k times 5,600. And I'm going to divide both sides of the equation by a naught, which will completely drop out of the problem at this point. And I'm left with 0.5 equals e to the 5,600k. And then in order to get to that k, I'm going to use the natural log to get k out of the exponent position. And I'm going to apply the natural log to both sides of the equation. This natural log is the exponent I need to apply to the base of the log. The base of the log is an unwritten e to get e to the 5,600k. So that's simply 5,600k. So when I start with some value, in this case 5,600k, I apply it to an exponential function whose base is e, and then I turn around and apply the logarithmic function whose base is e. I have applied a function followed by its inverse. I get back what I started with. So natural log of 0.5 is 5,600k. When I divide both sides of the equation by 5,600, I'm then able to solve for k. So I find out that k is the natural log of 0.5 over 5,600. And when I do my calculations on that, I see, and I know I'm going to get a negative. I get approximately negative 0.0000143. And I'm now going to refine my function by saying a equals whatever the initial amount is times e to the negative 0.000143 t. Now, I want to find how long it takes for this to decay to 45% of the original amount. So to do that, I'm going to replace A with 0.45 or 45% of the initial amount. And I'm going to just put KT here for a minute. I'm going to divide both sides by A sub 0. That divides right out of the problem. And I'm left with 0.45 equals e to the KT. I'm going to apply the natural log to both sides of the equation. And the natural log of e to the KT is simply KT. So the natural log of 0.45 is KT. So T then is obtained by dividing both sides of the equation by K. So now I'll put the K value in. Natural log of 0.45 is negative 0.000143. And I'll use my calculating device to find out that value. And I get that that is about 5,583. So notice that's my approximation of T. So it takes about 5,583 years, or actually the question is how old is the bone? So let's just answer that more directly. The bone is about 5,583 years old. And that's how long it takes the carbon-14 to decrease to about 45%. And we knew before we even started, if we didn't get a number smaller than 5,600, that's how long it takes for it to decrease to half. We knew that we were doing something wrong. Okay, so the third problem is Newton's law of cooling, and the function that results from this law is given. T is the time it takes for an object to cool from temperature T0, the initial temperature, to temperature T, and C is the surrounding air temperature, and K is a positive constant associated with the properties of the cooling object or substance. So we're going to allow, given the information, T time to be 10, and of course it's measured in minutes. For this part of the problem, we're going to find our K, and we're going to let the temperature that the object cools to, so the capital T, we're going to allow that to be 75, and our initial temperature is the 90 degrees, or 90. And then we know that, so we've got everything here except the surrounding air temperature, which is 25. So this is going to allow me to find K. So 75 equals 25 plus 90 minus 25, e to the minus k times 10. So 75 equals 25 plus 65 e to the minus 10k. And my goal is to isolate the exponential. So 50 equals 65 e to the negative 10k. Divide both sides by 65 to get that exponential isolated. And 50 over 65 equals e to the negative 10k. And apply the natural log to both sides of the equation. When I apply the natural log to e to the minus 10k, I basically get back the minus 10k. And to solve for k, I'm going to divide both sides of the equation by minus 10. And that allows me to find the k and approximate it. So k is approximately 0.026236. And now I can answer the question, when will the temperature be 50 degrees Celsius? So in other words, capital T is now 50. And remember, little t is what I'm trying to find. The surrounding medium is still 25. The initial temperature is still that 90 degrees that the object was heated to, and the surrounding air temperature is 25, and my K, of course, is what I just found. And I'm trying to find T. All right, so that's my problem, and I am going to take the formula and just use it. Right, so we're going to replace T with 50. That's the temperature we're going to cool down to. The surrounding air temperature is 25. The initial temperature is the 90. Again, the surrounding air temperature is 25. E to the minus 0.026236 T. And we're trying to find T. 50 equals 25 plus 65 e to the minus 0.026236 t. And again, we want to isolate the exponential. So we're first going to subtract 25 from both sides. And we get 25 equals 65 e to the minus 0.026236 t. And now we're going to divide both sides by 65 to completely isolate the exponential. And we obtain 25 over 65 equals e to the negative 0.026236 t. And I'm going to apply the natural log to both sides of the equation. And I know that simply gives me the exponent. And to solve this for T, I'm going to be dividing by K. So that's going to give me my T value. And let's do the calculation. And we get an answer that rounds to about 36 minutes. So it takes about 36 minutes to cool to 50 degrees Celsius. And then if we look back at the information, we knew that it took 10 minutes for the object to cool to 75 degrees. So we expect that it's going to take more than 10 minutes to cool further to 50 degrees. So that makes a lot of sense.